Tonight we're going to explore what happens when matter is pushed to the absolute breaking point. Not crushed by a hydraulic press, not compressed in a laboratory, but squeezed by gravity so powerful that atoms themselves are destroyed. Inside a neutron star, matter is packed so tightly that a single teaspoon weighs more than every building in New York City combined. At these densities, the familiar structure of atoms, electrons orbiting a nucleus, the architecture that makes up everything you've ever touched, simply cannot survive. Electrons are driven into protons, nuclei dissolve, and the deeper you go, the stranger things become. Because at the very center of a neutron star, even the particles that replace the atoms may themselves begin to break apart into something else entirely. Something physicists are still struggling to understand. Tonight, we're going inside. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you already understand. Matter. The stuff you're made of. The stuff everything is made of. Right now, you're sitting somewhere, maybe in a chair, maybe on a couch, maybe lying in bed. Whatever surface you're resting on feels solid. Your body feels solid. The floor beneath you, the walls around you, the device you're watching this on. All of it feels firm and real and substantial. But here's what's actually happening at the atomic level. Every solid object you've ever touched is almost entirely empty space. An atom, the basic unit of all ordinary matter, consists of a tiny nucleus surrounded by a cloud of electrons. And when I say tiny, I mean almost incomprehensibly tiny relative to the atom itself. If you could scale an atom up to the size of a football stadium, the nucleus at the center would be about the size of a marble sitting on the 50-yard line. Everything else, the entire volume of the stadium, would be empty, just electrons buzzing around somewhere in the upper seats, impossibly far from that little marble at the center. This means that the chair you're sitting on, which feels perfectly solid, is almost entirely nothing. The atoms in that chair are mostly empty space. Your hand, when it rests on the armrest, is mostly empty space pressing against more mostly empty space. The reason it feels solid is because of electromagnetic forces between the electron clouds of adjacent atoms. Those forces push back when atoms get too close. It's not that matter is packed tightly together, it's that electrical repulsion between electron clouds creates the illusion of solidity. In reality, there's an enormous amount of room inside every atom, an enormous amount of wasted space. And this is the key to understanding what happens inside a neutron star. Because a neutron star is what you get when the universe finds a way to crush all of that empty space out of matter. When gravity becomes so overwhelmingly powerful that it collapses the vast emptiness inside atoms, forces electrons into places they were never meant to go, and compresses what's left into something so dense that it defies every intuition you have about how matter should behave. But before we get to that extreme, we need to understand how such an object comes to exist in the first place. And that means we need to talk about stars. Not as points of light in the night sky, but as physical objects. Massive, violent, and ultimately doomed. A star is a battle. That's the simplest way to describe it. From the moment a star is born to the moment it dies, it exists in a constant struggle between two opposing forces. On one side is gravity, pulling everything inward, trying to crush the star down to the smallest possible size. On the other side is the energy generated by nuclear fusion in the star's core, pushing outward, resisting the collapse. For most of a star's life, these two forces are almost perfectly balanced. Gravity squeezes inward, fusion pushes outward. The star holds steady, shining, stable, living. Our sun has been doing this for about 4.5 billion years. Deep in its core, where temperatures reach roughly 27 million degrees Fahrenheit and pressures are about 260 billion times the atmospheric pressure at Earth's surface, hydrogen atoms are being fused into helium. Every single second, the sun converts approximately 600 million tons of hydrogen into helium. In the process, a small fraction of that mass, about 4 million tons per second, is converted directly into energy, according to Einstein's famous equation relating energy and mass. That energy radiates outward through the sun's layers, creating the outward pressure that holds the star up against its own gravity. This is how every star works. Gravity wants to collapse it, fusion fights back. As long as there's fuel to burn, the star survives. But fuel doesn't last forever, and when it runs out, gravity wins. What happens next depends entirely on how massive the star was to begin with. Our Sun is a relatively modest star. When it exhausts its hydrogen fuel in about 5 billion years, it will swell into a red giant, shed its outer layers, and leave behind a dense remnant called a white dwarf. A white dwarf is impressive by everyday standards. It contains roughly the mass of the Sun, compressed into an object about the size of Earth. A teaspoon of white dwarf material would weigh roughly 5 tons. That's dense. But it's nothing compared to what happens when a much more massive star dies. Stars that are roughly 8 to 20 times more massive than the Sun, sometimes even more, live dramatically different lives. They burn hotter, brighter, and faster. A star 10 times the mass of the Sun doesn't live 10 times shorter than the Sun. It lives hundreds of times shorter. While the Sun will burn steadily for about 10 billion years total, a star with 20 times the Sun's mass might exhaust its fuel in only about 10 million years. That's roughly 1,000th the Sun's lifespan. These massive stars are burning through their fuel at a prodigious rate. Because their cores are so much hotter and denser, the fusion reactions proceed far more rapidly. And here's the crucial difference. While a star like the Sun can only fuse hydrogen into helium before running out of options, massive stars can keep going. When the hydrogen in the core is spent, gravity compresses the core further, heating it until helium begins fusing into carbon and oxygen. When the helium is used up, gravity squeezes again, and carbon begins fusing into neon and magnesium. Then neon fuses into oxygen and magnesium. Then oxygen fuses into silicon and sulfur. Each stage requires higher temperatures to ignite than the one before it. Hydrogen fusion happens at tens of millions of degrees. Helium fusion requires roughly 100 million degrees. Carbon ignites at about 500 million degrees. Oxygen needs roughly 1 billion degrees, and silicon fusion demands approximately 3 billion degrees. The star's core is getting hotter, denser, and more desperate with each stage, and each new fuel lasts for a dramatically shorter time than the one before. Hydrogen burning might last millions of years. Helium burning lasts perhaps a few 100,000 years. Carbon burning might last a few 100 years. Oxygen burning lasts maybe a year, and the final stage, silicon burning, lasts roughly 1 day. Think about the acceleration of that timeline. Millions of years, then hundreds of thousands, then hundreds, then one, then a single day. The star is sprinting toward its own death, each fuel source depleted faster than the last. 1 day. After millions of years of steady burning through progressively heavier elements, the star reaches its final fuel in a single frantic day. Silicon fuses into iron and nickel, and then something catastrophic happens. Everything stops. Iron is the end of the line for nuclear fusion. Every element lighter than iron releases energy when it fuses into heavier elements. That's what has been keeping the star alive this whole time. Fusion releases energy. That energy creates outward pressure, and outward pressure holds the star up against gravity. But iron is different. Fusing iron doesn't release energy, it absorbs energy. It actually takes energy away from the core instead of providing it. When the core fills with iron, it's like a furnace that has run out of fuel and started consuming its own heat. The energy source that has been supporting the star against gravitational collapse for millions of years suddenly vanishes. What happens next takes less than a second. The iron core, no longer supported by fusion energy, begins to collapse under its own gravity. The collapse is extraordinarily violent. The core falls inward at speeds approaching 1/4 of the speed of light. That's roughly 75,000 kilometers per second. In roughly 1/10 of a second, a core that was approximately the size of Earth, roughly 8,000 miles across, collapses down to a sphere roughly 12 miles across. Try to picture that. An object the size of an entire planet crushing itself into something the size of a small city in a fraction of a second. Nothing in your everyday experience prepares you for this kind of violence. No explosion you've ever seen, no natural disaster, No collision or crash comes anywhere close. This is the single most energetic event that can happen to a single object in the known universe, short of falling into a black hole. The gravitational energy released during this collapse is staggering. More energy is released in those few seconds than the star produced during its entire multi-million-year lifetime. Most of this energy is carried away by neutrinos, ghostly particles that barely interact with matter. The neutrino burst from a core collapse is so intense that for a few seconds, the dying star radiates more energy in neutrinos alone than all the stars in its own galaxy are radiating in light combined. That's not an exaggeration. For a brief moment, a single dying star outshines the combined light output of hundreds of billions of stars, just in neutrinos. The outer layers of the star, which are still falling inward, slam into the newly formed ultra-dense core and bounce off in a catastrophic shockwave. This shockwave, energized by the neutrino flux from the core, tears through the star's outer layers and blows them apart in a supernova explosion. The explosion is one of the most violent events in the universe. For a few weeks, a single supernova can outshine an entire galaxy containing hundreds of billions of stars. If a supernova occurred at the distance of the nearest star to our Sun, roughly 4 light-years away, it would be visible during the daytime and bright enough to cast shadows at night. But we're not interested in the explosion, we're interested in what's left behind. Because at the center of all that destruction, where the core collapsed in a fraction of a second, sits something extraordinary. A neutron star. The core didn't just collapse, it was compressed so violently that the very structure of matter was fundamentally altered. During the collapse, conditions became so extreme that the normal rules governing atomic structure simply stopped applying. We'll explore exactly how this transformation works in detail shortly, but for now, understand that what remains after the collapse is no longer made of ordinary atoms. It's something else entirely, something far denser, far stranger, and far more extreme than any form of matter you've ever encountered. A neutron star typically contains between about 1.5 and 2 times the mass of our Sun, sometimes slightly more. All of that mass is packed into a sphere roughly 12 miles across. 12 miles. That's roughly the distance from one side of a mid-sized city to the other. You could drive across a neutron star in about 15 minutes if there were a road, which there obviously isn't, because the surface conditions would obliterate anything known to science long before you arrived. The density of a neutron star is almost impossible to communicate in a way that feels real, but let me try. Take a sugar cube, a normal sugar cube, the kind you might drop into a cup of coffee. It's small enough to sit on the tip of your finger. Now imagine that tiny cube filled not with sugar, but with neutron star material. That single sugar cube would weigh roughly 400 million tons. Let me put that number in context. The Great Pyramid of Giza, one of the most massive structures humans have ever built, weighs roughly 6 million tons. A sugar cube of neutron star material outweighs the Great Pyramid by a factor of nearly 70. It would weigh more than every car, truck, bus, train, and airplane currently in existence on Earth combined. All of that mass in a cube you could hold between your fingertips. If you somehow dropped it, and obviously you couldn't hold it because the gravitational pull of that sugar cube alone would be immense, it wouldn't just fall to the ground. It would fall through the ground, through the crust, through the mantle, straight to the center of the Earth, because nothing on our planet has the structural strength to resist that kind of density. The average density of a neutron star is approximately 400 million tons per cubic centimetre. That is roughly 2 to 3 times the density of an atomic nucleus. An atomic nucleus is already the densest form of ordinary matter known to physics. The nucleus of an atom, that marble on the 50-yard line we talked about earlier, is packed incredibly tightly. Protons and neutrons inside a nucleus are squeezed together at densities of roughly 230 million tons per cubic centimetre. That's the densest that normal nuclear matter gets, and a neutron star exceeds even that. This is a critical point that deserves emphasis. A neutron star is not just dense, it is denser than the interior of an atomic nucleus. It has surpassed the density of the densest thing that exists under normal conditions anywhere in the universe. This means the matter inside a neutron star cannot be ordinary nuclear matter in the way we understand it from studying nuclei in laboratories. Something else must be happening. The matter is being pushed into a regime where our laboratory experience with nuclear physics starts to lose its footing. To appreciate just how far beyond everyday experience this is, let's build a scale of densities. Start with air. The air you're breathing right now has a density of roughly 1.25 kilograms per cubic meter. That's very thin. You can move through it easily. You barely notice it's there. Water is about 800 times denser than air, roughly 1,000 kilograms per cubic meter. You can still move through it, but you feel the resistance. Swimming is harder than walking. Water pushes back. Iron, one of the densest common materials, has a density of about 7,800 kilograms per cubic meter, almost 8 times denser than water. You can't move through iron at all. It feels absolutely solid, impenetrable. The densest naturally occurring element on Earth is osmium, at roughly 22,500 kilograms per cubic meter, about 3 times denser than iron. If you held a block of osmium, you'd be startled by how heavy it felt for its size. It would feel wrong, like someone had played a trick on you and secretly filled it with something impossibly heavy. Now let's leave Earth behind. The core of the Sun has a density of roughly 150,000 kilograms per cubic meter, about 7 times the density of osmium. This is hot, compressed plasma, not something you'd encounter in everyday life, but still within the range of normal matter. Atoms still exist here. They're ionized, stripped of their electrons, but the nuclei are still intact and separated from each other. A white dwarf pushes much further. The typical density of a white dwarf is about 1 billion kilograms per cubic meter. That's roughly 10,000 times denser than the Sun's core. At this point, atoms have been stripped of their electrons completely, and the electrons form a dense sea called a degenerate electron gas. The nuclei are packed close together, much closer than in normal matter, but they're still individual nuclei. Atomic structure is heavily distorted, but some form of it still persists. A white dwarf is the densest object that can exist while still maintaining anything resembling atomic structure. It's the end of the road for matter that doesn't get pushed further, and for a long time, physicists thought white dwarfs might be the densest objects in the universe. They were wrong. And then there's a neutron star. At roughly 1 trillion to 1 quintillion kilograms per cubic meter, depending on how deep inside you go, that is 1,000 to 1 billion times denser than a white dwarf. A white dwarf was already 10,000 times denser than the Sun's core. The Sun's core was already denser than any material on Earth. Each step on this ladder represents a leap of many orders of magnitude, and a neutron star sits at the very top, at densities where the matter no longer resembles anything we've ever studied directly. This isn't just compressed matter. This is matter that has been fundamentally restructured by forces beyond anything reproducible in a laboratory. We are dealing with conditions that don't exist anywhere else in the observable universe, except inside these objects, and perhaps briefly during the collisions between them. The gravity on the surface of a neutron star reflects these extreme conditions. The surface gravitational acceleration on a typical neutron star is roughly 200 billion times the gravitational acceleration on Earth's surface. On Earth, if you drop a ball, it accelerates toward the ground at about 9.8 meters per second squared. On a neutron star, that same ball would accelerate at roughly 2 trillion meters per second squared. If you could somehow stand on the surface of a neutron star, which you couldn't because you'd be killed instantly in dozens of different ways, you would weigh about 200 billion times more than you weigh on Earth. A person weighing 150 pounds on Earth would weigh roughly 30 trillion pounds on the surface of a neutron star. Your body would be flattened into a film of atoms thinner than a sheet of paper in a fraction of a microsecond. Objects falling onto a neutron star reach extraordinary speeds. Material falling from a great distance accelerates to roughly half the speed of light by the time it hits the surface. That's about 150 million meters per second. When matter strikes the surface at these speeds, the kinetic energy is converted into radiation, producing X-rays visible across the galaxy. This is actually how we detect many neutron stars. They're too small and too far away to see directly with optical telescopes. A 12-mile wide object light years away is far too small to resolve. But when matter falls onto them from a companion star or from surrounding debris, the impact generates X-rays so powerful that space-based X-ray telescopes can detect them across thousands of light years. The escape velocity from a neutron star's surface is roughly 150,000 to 200,000 kilometers per second. That is between half and two-thirds the speed of light. For comparison, the escape velocity from Earth's surface is about 11.2 kilometers per second. The escape velocity from the Sun's surface is roughly 618 kilometers per second. A neutron star's escape velocity is hundreds of times greater than the Sun's. This means that to launch anything off the surface of a neutron star, you would need to accelerate it to a significant fraction of light speed. Nothing leaves a neutron star easily. The magnetic fields on neutron stars are equally extreme. A typical neutron star has a magnetic field roughly 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have magnetic fields up to 1,000 times stronger still, reaching roughly 1 quadrillion times Earth's field strength. These magnetic fields are so intense that they would distort the shapes of atoms, stretching them into long, thin cylinders aligned with the field. At the surface of a magnetar, the magnetic field is strong enough to affect the vacuum of space itself, making empty space behave like a lens that bends and polarizes light passing through it. Neutron stars also spin rapidly. Because the collapsing core conserves angular momentum, the same way a figure skater spins faster by pulling their arms in, the resulting neutron star rotates at extraordinary rates. The original stellar core might have been rotating once every few hours or days, but when all that mass collapses from the size of Earth to the size of a city, the rotation speeds up enormously. Most neutron stars spin several times per second when they're first born. Some spin much faster. The fastest known neutron star, a millisecond pulsar, designated PSRJ 1748-2446 AD, rotates 716 times per second. The surface at its equator moves at roughly 1/6 of the speed of light. If you placed a point on its equator, that point would complete a full rotation in about 1.5 milliseconds. In the time it takes you to blink your eye, this neutron star has rotated roughly 200 times. The centrifugal forces at the equator of such an object are immense, and the fact that the star holds together at all is a testament to the extraordinary strength of the gravitational and nuclear forces operating within it. All of these numbers, the density, the gravity, the magnetic fields, the rotation, they're telling us the same thing. A neutron star is an object that exists at the extreme edge of what matter can do before it crosses over into something else entirely. It's not quite a black hole. A black hole forms when gravity wins completely and matter collapses beyond any known force's ability to resist. A neutron star sits just below that threshold, at the boundary where matter is compressed as far as it can go, while still managing to push back and maintain some kind of structure. And this is the question that drives everything we're going to explore. What kind of structure? What does matter actually look like when it's squeezed this hard? You know what normal matter looks like? Atoms with electron clouds and nuclei. You know what white dwarf matter looks like? A sea of degenerate electrons with bare nuclei embedded in it. But neutron star matter is something beyond both of these. It has been pushed into a regime where atoms cannot exist, where even the relationship between electrons and protons has been fundamentally altered, and where the deeper you go, the more uncertain we become about what's really happening. We know the broad picture. We know that somewhere inside a neutron star, the familiar building blocks of atoms have been dismantled and rebuilt into something radically different. We know that the outer regions are different from the inner regions, and the innermost core is different from everything else. We know that the conditions deep inside exceed what any laboratory on Earth has ever achieved, or is ever likely to achieve. And we know that whatever is happening in there, it represents one of the most extreme physical environments in the entire universe. But the details are where things get fascinating. And to understand those details, we need to go inside, layer by layer. We need to start at the surface and work our way down, watching as familiar physics gives way to progressively stranger behavior. We need to see how electrons are forced into protons, how neutrons flood out of disintegrating nuclei, how nuclear matter arranges itself into shapes that would seem absurd in any other context, and ultimately, how even the neutrons themselves may begin to lose their identity at the crushing pressures found at the core. The story of what happens to matter inside a neutron star is the story of physics being pushed to its absolute limits. It's the story of nature finding out what happens when you take the structures that make up everything in the observable universe and squeeze them harder than they were ever meant to be squeezed. And it's a story that, even today, remains incomplete. Because the deepest interior of a neutron star, the conditions at the very center, remain one of the most profound open questions in all of physics. Let's go inside and find out what we know and what we're still trying to figure out. To understand what's happening inside a neutron star, we first need to understand what matter looks like when it hasn't been crushed. We need to understand the architecture of ordinary atoms, the structure that everything around you relies on, because only then will you appreciate what it means for that architecture to be destroyed. An atom, at its most basic, is a nucleus surrounded by electrons. The nucleus sits at the center, incredibly small, incredibly dense, containing virtually all of the atom's mass. It's made of protons and neutrons, particles held together by the strong nuclear force, which is the most powerful force in nature at short range. Protons carry a positive electrical charge. Neutrons carry no charge at all. Together they form a tight, compact ball at the heart of every atom. Around this nucleus, at relatively enormous distances, orbit the electrons. Electrons are tiny compared to protons and neutrons. A single proton is about 1,836 times more massive than a single electron. Electrons carry a negative electrical charge, which is attracted to the positive charge of the protons in the nucleus. This electromagnetic attraction is what keeps electrons bound to the atom. It's what gives atoms their structure, their size, their chemical behavior. The arrangement of electrons around the nucleus isn't random. Electrons organize themselves into shells and orbitals according to the rules of quantum mechanics. Each shell can hold a specific number of electrons. The first shell holds 2, the second holds 8, the third holds 18, and so on. These shells are not physical structures like the shell of an egg. They're quantum mechanical probability distributions, regions of space where an electron is likely to be found. But the rules governing them are absolute. You cannot add more electrons to a full shell. The mathematics of quantum mechanics forbids it. The outermost electrons, the ones in the highest energy shell, determine almost everything about how an atom interacts with other atoms. They determine an element's chemical properties, what bonds it can form, what molecules it can create, whether a substance is a metal, or a gas, or a crystalline solid. All of chemistry, all of the molecular behavior that makes life and matter and the physical world possible, comes down to the behavior of these outermost electrons. This electron structure is what gives matter its volume. Remember the football stadium analogy. The nucleus is the marble on the 50-yard line. The electrons are buzzing around somewhere in the distant stands. Almost all of the atom's volume is defined not by the nucleus, but by the electron cloud. The nucleus accounts for the mass. The electrons account for the space. When you touch a table and it feels solid, you're feeling the electron clouds of your hand's atoms being repelled by the electron clouds of the table's atoms. It's electrons all the way down. The solidity, the volume, the tangibility of everything you've ever touched is a product of electron structure. And here's what matters for our story. That electron structure, the very thing that gives matter its volume and its familiar properties, can be destroyed. Under sufficient pressure, the elaborate architecture of electron shells and orbitals can be crushed out of existence. The electrons don't disappear, they can't. They're fundamental particles with nowhere to go. But they lose their structure. They stop orbiting individual nuclei. They stop forming shells and bonds and molecules. They become something different, something unbound. This is what happens inside a white dwarf, and understanding white dwarfs is essential to understanding what comes next. A white dwarf forms when a star like our Sun dies. The star sheds its outer layers, and the core that remains is no longer producing energy through fusion. Gravity compresses this core, squeezing it tighter and tighter. At first, the atoms resist. Their electron clouds push back against the compression. But gravity keeps squeezing, the pressure mounts, and eventually, the electron clouds are crushed, the atoms are ionized, electrons are stripped away from their nuclei entirely. Instead of orbiting individual atoms in neat quantum shells, the electrons form a dense sea, a kind of electron soup, filling the spaces between the bare nuclei. Now, at this point, something remarkable happens. The electrons begin to resist further compression, but not through ordinary electromagnetic repulsion. They resist through a quantum mechanical effect called electron degeneracy pressure. This is one of the most important concepts in astrophysics, and it comes directly from a fundamental rule of quantum mechanics called the Pauli exclusion principle. The Pauli exclusion principle, formulated by physicist Wolfgang Pauli in 1925, states that no two identical fermions can occupy the same quantum state simultaneously. Fermions are a class of particles that includes electrons, protons, and neutrons. The exclusion principle means that every electron in a system must have a unique set of quantum properties. No two electrons can have exactly the same position, momentum, and spin at the same time. They must differ in at least one property. In everyday matter, this principle shapes atomic structure. It's the reason electrons fill different energy levels, rather than all piling into the lowest one. It's the reason atoms have different sizes and different chemical properties. It's one of the most fundamental rules governing matter. In a white dwarf, the Pauli exclusion principle takes on a new role. The electrons have been stripped from their atoms and packed together at extreme density. As gravity tries to compress them further, the electrons are forced into higher and higher energy states, because the lower energy states are already occupied. You can't put two electrons in the same state, so as you pack more electrons into a smaller volume, each new electron must occupy a higher energy level than the ones already present. These high-energy electrons exert an outward pressure. This is electron degeneracy pressure. It's not caused by heat or temperature. It's a purely quantum mechanical effect arising from the fundamental impossibility of putting identical fermions in the same state. Electron degeneracy pressure is what holds up a white dwarf. It's what prevents gravity from compressing the star further. It's an extraordinarily effective form of support. A white dwarf can contain roughly the mass of the Sun in a volume the size of Earth, and electron degeneracy pressure holds it stable against gravitational collapse without any energy input at all. No fusion is needed, no heat source is required. The quantum mechanical stubbornness of electrons refusing to share quantum states is enough to resist the gravitational pull of an entire star's worth of mass. But there's a limit. In 1930, a young Indian physicist named Subrahmanyan Chandrasekhar, just 19 years old at the time, was travelling by ship from India to England to begin his graduate studies at Cambridge. During the long sea voyage, with weeks stretching ahead of him, Chandrasekhar passed the time by working through calculations about the physics of white dwarfs. He combined the newly developed theories of quantum mechanics with Einstein's special relativity and applied them to the question of how dense matter behaves under extreme gravitational compression. The calculations he performed on that ship would change astrophysics forever. Chandrasekhar asked a simple but profound question. Is there a maximum mass that electron degeneracy pressure can support? Is there a point where gravity becomes too strong for even this quantum mechanical force to resist? Could there be a stellar remnant so massive that the electrons simply could not push back hard enough? The answer was yes. Chandrasekhar calculated that electron degeneracy pressure can support a white dwarf only up to about 1.4 times the mass of the Sun. Above this mass, now called the Chandrasekhar limit in his honour, gravity overwhelms electron degeneracy pressure completely. The electrons simply cannot generate enough outward pressure to hold the star up, no matter how high their energy states are pushed. The reason is rooted in special relativity. As electrons are forced to higher and higher energies, they approach the speed of light. But nothing can exceed the speed of light. The electrons hit a relativistic wall. Their energy keeps climbing, but the additional pressure they generate becomes less and less effective at resisting further compression. Gravity gains the upper hand. If a white dwarf somehow gained enough mass to exceed this limit, the electrons would lose their battle against gravity, and the star would collapse. This was a revolutionary finding. It meant that white dwarfs had a maximum mass. It meant that sufficiently massive stellar remnants could not exist as white dwarfs. They had to become something else. Something denser. Something where a different kind of pressure takes over. And this is exactly what happens during the formation of a neutron star. When the iron core of a massive star collapses, the density climbs rapidly past white dwarf levels. Electron degeneracy pressure, which works perfectly for white dwarfs, is completely insufficient here. The core mass is well above the Chandrasekhar limit. Gravity is far too powerful. The electrons are being squeezed into an ever smaller volume, their energies climbing higher and higher as the Pauli exclusion principle forces each one into increasingly energetic quantum states. The pressure is rising, but it's not rising fast enough. Gravity is winning. And then something extraordinary begins to happen. The electrons become so energetic that they start interacting with the protons in the nuclei around them. When an electron reaches sufficiently high energy, it can be captured by a proton through a process called inverse beta decay. The electron combines with the proton, and the two transform into a neutron and a neutrino. The electron and the proton simply cease to exist as separate particles. They merge into a neutron, and the neutrino flies away at nearly the speed of light, carrying energy out of the collapsing core. This process is governed by the weak nuclear force, one of the four fundamental forces of nature. The weak force is responsible for certain types of radioactive decay and for transformations between different types of quarks. In inverse beta decay, an up quark inside the proton is converted into a down quark, mediated by the exchange of a W boson. The result is that the proton, which had two up quarks and one down quark, becomes a neutron with one up quark and two down quarks. The electron is consumed in the process, and the neutrino carries away the balance of energy and momentum. It's a fundamental rearrangement of matter at the subatomic level, forced into existence by the overwhelming pressure of gravitational collapse. This is worth pausing on. An electron and a proton, two of the most fundamental building blocks of ordinary matter, are being forced to combine. This doesn't happen under normal circumstances. Under everyday conditions, neutrons are actually slightly heavier than a proton and electron combined, so it takes energy to create a neutron from a proton and an electron. Under normal circumstances, free neutrons are unstable, they decay. A free neutron sitting in empty space will spontaneously convert into a proton, an electron, and an antineutrino, with a half-life of about 10 minutes. This is ordinary beta decay, and it's one of the most well-studied processes in nuclear physics. Under normal conditions, nature prefers protons and electrons to neutrons. But inside a collapsing stellar core, conditions are the opposite of normal. The electrons have been compressed to such extreme energies that they actually have more energy than the mass difference between a neutron and a proton-electron pair. The reaction becomes energetically favorable in the opposite direction. Instead of neutrons decaying into protons and electrons are being driven into protons to create neutrons. The normal direction of the reaction has been reversed by the sheer force of gravitational compression. And the process feeds on itself. Every time an electron is captured by a proton, one electron and one proton are removed from the mix. This means one fewer electron contributing to electron degeneracy pressure. The pressure drops slightly, which allows gravity to compress the core a little more, which forces the remaining electrons to even higher energies, which causes more electrons to be captured by protons. It's a runaway process, a cascade, a feedback loop that accelerates the transformation. More and more electrons are consumed. More and more protons are converted into neutrons. The core becomes increasingly neutron-rich. What started as a mix of roughly equal numbers of protons and electrons alongside neutrons in iron nuclei quickly tips toward an overwhelming dominance of neutrons. The matter is being fundamentally transformed, particle by particle, from the inside out. The neutrinos produced by this process carry enormous amounts of energy. During the collapse, roughly 99% of the gravitational binding energy of the forming neutron star, about 3 times 10 to the 46 joules, is carried away by neutrinos. This is an almost unimaginable amount of energy. It's roughly 200 times more energy than the Sun will produce over its entire 10 billion year lifetime, released in a burst lasting roughly 10 seconds. The neutrino burst from a core collapse supernova is one of the most energetic phenomena in the universe. We actually detected neutrinos from a supernova for the first, and so far only time, in 1987, when supernova 1987A exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, about 168,000 light-years from Earth. Detectors in Japan and the United States picked up a total of roughly 25 neutrinos from the event. Just 25. But that tiny handful confirmed decades of theoretical predictions about how core collapse works. Now let's think about what the matter looks like as this process unfolds. Because the transformation doesn't happen all at once, it proceeds gradually as you move deeper into the neutron star, and the structure of matter changes dramatically from the surface to the interior. The outermost layer of a neutron star is its surface, sometimes called the envelope or atmosphere. This layer is extraordinarily thin, perhaps only a few centimeters to a meter thick. It's made of ordinary matter, mostly hydrogen and helium, possibly some heavier elements, arranged in a form that's heavily affected by the intense magnetic field and gravity, but still recognizable as ordinary atomic matter. It's incredibly hot, typically about 1,000,000 degrees, but structurally, it's the most familiar part of the neutron star. Below the atmosphere lies the outer crust, a layer extending from the surface down to a depth of perhaps a few hundred meters. Here, conditions are already far beyond anything on Earth, but matter still retains some recognizable features. The atoms have been completely ionized, stripped of all their electrons, just as in a white dwarf. The bare nuclei arrange themselves into a crystalline lattice, a regular repeating three-dimensional grid, because the electrostatic repulsion between the positively charged nuclei and the attraction to the surrounding electron sea naturally produces an ordered structure. Think of it as a metallic crystal, similar in principle to how iron atoms arrange themselves in a block of solid iron, except the nuclei are packed far more tightly, and the electrons between them form a dense degenerate gas. The nuclei in the outer crust are neutron-rich isotopes. Ordinary iron on Earth has 26 protons and 30 neutrons, but the nuclei in the outer crust have been squeezed so hard that inverse beta decay has already begun converting some of their protons into neutrons. The nuclei here might have the same number of protons as familiar elements, but far more neutrons than any stable isotope you'd find on Earth. They are exotic, neutron-bloated versions of elements like iron, nickel, selenium, and krypton. These isotopes would be wildly unstable under normal conditions. They would decay in fractions of a second. But inside the crust of a neutron star, they're held stable by the incredible pressure of their surroundings. There's nowhere for the extra neutrons to go. The environment forces stability on structures that would be impossible anywhere else. As you move deeper into the outer crust, the pressure increases, and the nuclei become more and more neutron-rich. At each depth, equilibrium is reached with a different isotope, each one containing progressively more neutrons relative to its protons. The nuclei are being steadily transformed. The ratio of neutrons to protons climbs higher and higher with depth. At the surface, you might find nuclei similar to iron-56, with 26 protons and 30 neutrons. Deeper in, you find isotopes with 40, 50, 60 or more neutrons packed around the same number of protons. These nuclei are enormous by normal standards, swollen with neutrons they wouldn't have under any natural conditions. And then, at a depth of a few hundred meters and a density of roughly 400 trillion kilograms per cubic meter, something critical happens. The nuclei become so saturated with neutrons that they physically cannot hold any more. There's a limit to how many neutrons the strong nuclear force can bind within a single nucleus, even under these extraordinary pressures. When that limit is exceeded, neutrons begin leaking out. They drip out of the nuclei like water overflowing from an overfilled glass. This is called the neutron drip point, and it marks the boundary between the outer crust and the inner crust. It's one of the most important phase transitions in all of astrophysics. The neutron drip point is one of the most important transitions inside a neutron star. Above it, in the outer crust, all the neutrons are still bound inside nuclei. The matter consists of neutron-rich nuclei sitting in a lattice, surrounded by a sea of degenerate electrons. It's extreme, but the nuclei are still intact. They're strained and bloated, but they're holding together. Below the neutron drip point, the situation changes fundamentally. Now the matter consists of three components. There are still nuclei, even more bloated with neutrons than before. There is still a sea of degenerate electrons, but there's also now a gas of free neutrons filling the space between the nuclei. These free neutrons have been squeezed out of the nuclei by the relentless pressure and have nowhere to go but the spaces in between. They wander between the nuclei, forming a neutron fluid that coexists with the nuclear lattice in a way that has absolutely no counterpart in any terrestrial material. This is a kind of matter that has no analogue anywhere on Earth or anywhere else in the universe under normal conditions. Nothing in your experience corresponds to it. There is no laboratory that can recreate it. It's a crystal lattice of enormous neutron-rich nuclei immersed simultaneously in both a degenerate electron gas and a free neutron gas. Three populations of particles coexisting in a state that exists nowhere else in the observable universe except inside neutron stars. As you continue deeper into the inner crust, the proportion of free neutrons increases steadily. At the neutron drip point, maybe a few % of the neutrons are free. Deeper down, the fraction climbs. 10%, 20%, 50%. More and more neutrons are being squeezed out of the nuclei. The nuclei are becoming increasingly neutron-rich, but they're also losing neutrons to the surrounding gas faster than inverse beta decay can produce new ones inside. The nuclei are literally dissolving from the outside, shedding neutrons into the surrounding space like an ice cube melting in warm water, except the melting agent here is pressure, not heat. Simultaneously, the nuclei themselves are getting larger. They're absorbing more and more neutrons, swelling to enormous size. Under normal conditions, the largest stable nucleus is lead-208, with 82 protons and 126 neutrons. In the deep inner crust of a neutron star, nuclei might contain hundreds of neutrons. They are colossal by nuclear physics standards, structures that would be impossible under any other circumstances, held together only by the crushing pressure of their environment. As density continues climbing, something else changes. The degenerate electrons that were so important in the outer layers are becoming less and less significant. Remember, inverse beta decay has been steadily converting electrons and protons into neutrons. There are fewer and fewer electrons as you go deeper because they keep getting consumed. The electron degeneracy pressure, which was the dominant support mechanism in white dwarfs and still played a role in the outer crust, is fading. It's being replaced by something else. Neutron degeneracy pressure. The same Pauli exclusion principle that prevented electrons from sharing quantum states now applies to the neutrons. Neutrons are fermions too. They obey the same exclusion principle. As the free neutron gas becomes denser, the neutrons are forced into higher and higher energy states, and they begin generating their own degeneracy pressure. This neutron degeneracy pressure, along with the strong nuclear force interactions between neutrons, is what ultimately holds up a neutron star against gravity. This is the fundamental shift. In a white dwarf, electrons resist gravity. In a neutron star, neutrons resist gravity. The baton has been passed from one type of fermion to another at densities roughly 1,000,000 times higher, and then, at the base of the inner crust, at densities approaching roughly 230 billion kilograms per cubic centimeter, which is close to the density of ordinary nuclear matter, the remaining nuclei finally lose their identity entirely. The nuclei merge. They dissolve into the neutron gas surrounding them. The boundary between what was inside a nucleus and what was outside becomes meaningless. The individual nuclei, which had been getting progressively larger and more neutron-rich as you went deeper, finally touch each other and fuse into a continuous fluid. There are no more separate nuclei. There is no more lattice structure. There is just a vast, continuous sea of nuclear matter, predominantly neutrons, with a small admixture of protons and electrons. This transition from the crust to the core is the death of the atom in the truest sense. In the outer crust, you could still identify individual nuclei. You could still say this is an iron nucleus, this is a krypton nucleus. They were distorted, bloated, neutron-rich, sitting in conditions that would be impossible on Earth, but they were still nuclei. individual, discrete, identifiable objects. At the base of the crust, that identity is gone. The nuclei have merged into a continuous fluid. There are no more atoms. There are no more nuclei. There is only nuclear fluid, a material whose properties are determined by the strong nuclear force, quantum mechanics, and the intense gravitational pressure of the neutron star. Everything that chemistry depends on has been eliminated. Chemical reactions require electron orbitals. There are no electron orbitals. Molecular structure requires atoms bonding through shared or exchanged electrons. There are no atoms. Material properties like hardness, conductivity, transparency, all of these depend on the arrangement of atoms and the behavior of their electrons. None of these concepts apply here. The matter in the core of a neutron star is as different from the matter in your body as your body is different from a concept. It's not just a different material, it's a different kind of material, a different category of physical substance. The rules that govern it are not the rules of chemistry or even the rules of atomic physics. They are the rules of nuclear physics and quantum chromodynamics, the physics of quarks and gluons, the physics of the strong force operating at densities far beyond what any laboratory has ever achieved. And we're not even at the center yet. Everything I've described so far, the outer crust with its crystalline lattice, the inner crust with its dripping neutrons, the dissolution of nuclei at the crust core boundary, all of this happens in a shell that's perhaps 1 to 2 kilometers thick. The surface layers of the neutron star, the crust. Beneath it lies the outer core, then the inner core, stretching down another 8 or 9 kilometers to the center. And in those deeper layers, the conditions become even more extreme. The densities climb even higher. The pressures exceed anything that nuclear physics has been tested against. And the matter may begin to transform once again into something even stranger than a sea of neutrons. But that transformation, the truly exotic physics at the heart of a neutron star, is what comes next. For now, what matters is what we've just witnessed. The complete and total destruction of atomic structure. Every atom that existed in the original star, every nucleus that formed over millions of years of stellar fusion, every electron that orbited in its careful quantum shell, all of it has been dismantled. The electrons have been driven into the protons have become neutrons, the nuclei have swollen, leaked, and finally dissolved, and what remains is something no longer recognizable as the matter we know. It's something new, something the universe creates only under the most extreme conditions it can produce. And it sits there, 12 miles across, spinning hundreds of times per second, radiating X-rays into the darkness, a monument to what happens when gravity pushes matter past every breaking point it has. At the base of the crust, a kilometer or two below the surface, the last remnants of nuclear identity have been erased. The individual nuclei that survived deeper and deeper into the crust, swelling with neutrons, leaking particles into the surrounding fluid, have finally merged into one another. There are no more separate nuclei, no more lattice, no more crystalline structure. What remains is a continuous ocean of nuclear matter, stretching all the way to the center of the star. And this ocean is unlike anything that exists anywhere else in the known universe. The outer core of a neutron star begins at the base of the crust and extends inward for several kilometers. The matter here is predominantly neutrons. Roughly 90 to 95% of the particles are neutrons. The remaining 5 to 10% are protons and electrons in roughly equal numbers, maintained in equilibrium by the weak nuclear force. This ratio isn't accidental. It's the result of a delicate balance between competing physical processes. Here's how that balance works. If there were too many protons relative to neutrons, the electrons needed to maintain electrical neutrality would have very high energies, and inverse beta decay would convert protons and electrons into neutrons, reducing the proton fraction. If there were too few protons, the neutrons would have very high energies, and ordinary beta decay would convert neutrons back into protons and electrons. The system settles into a balance point called beta equilibrium, where the rates of both processes are equal and the composition is stable. At the densities found in the outer core, that equilibrium point is roughly 95% neutrons and 5% protons, with a matching 5% electrons to keep the total electric charge at 0. This is a profoundly neutron-dominated environment. Under normal conditions, an atomic nucleus typically has roughly equal numbers of protons and neutrons. Carbon-12 has 6 of each. Iron-56 has 26 protons and 30 neutrons. Slightly more neutrons, but the ratio is close to 1:1. In the outer core of a neutron star, the ratio is closer to 19:1. The matter has been overwhelmingly converted to neutrons. This is why these objects are called neutron stars. Now, what holds this object up against its own gravity? In a white dwarf, electron degeneracy pressure does the job. In a neutron star, the situation is more complex. Multiple forces contribute to resisting gravitational collapse, and understanding them requires understanding how nuclear matter behaves at these extraordinary densities. The first and most straightforward contribution comes from neutron degeneracy pressure. Neutrons, like electrons, are fermions. They obey the Pauli exclusion principle. No two neutrons can occupy the same quantum state at the same time. As the neutron fluid is compressed, neutrons are forced into higher and higher energy states because the lower states are already occupied. These high-energy neutrons exert an outward pressure, resisting further compression. This is directly analogous to electron degeneracy pressure in a white dwarf, but now it's the neutrons providing the support instead of the electrons. Because neutrons are roughly 1,836 times more massive than electrons, the physics plays out at vastly higher densities. But neutron degeneracy pressure alone isn't the whole story. Unlike electrons in a white dwarf, which interact primarily through electromagnetic forces, neutrons interact through the strong nuclear force, and the strong force changes everything. The strong nuclear force is the most powerful force in nature at short range. It's what holds protons and neutrons together inside atomic nuclei. Without the strong force, nuclei would fly apart instantly because the positively charged protons would repel each other electromagnetically. The strong force overcomes this repulsion and binds nucleons together. But it only operates at very short distances, roughly 1 femtometer, which is 1 quadrillionth of a meter, about the size of a proton itself. Beyond a few femtometers, the strong force drops to effectively zero. At the densities in the outer core of a neutron star, the average distance between neutrons is comparable to this range. The neutrons are packed so closely that they're all within each other's strong force range. Every neutron is constantly interacting with its neighbors through the strong force. This means the matter doesn't behave like a collection of individual particles bouncing off each other. It behaves like a fluid, a nuclear fluid, where the strong force creates complex correlations and interactions between all the particles simultaneously. And here's what makes this incredibly difficult to calculate. The strong nuclear force between two neutrons isn't simple. At very short distances, the force is repulsive. Push two neutrons too close together, and they resist fiercely. This short-range repulsion is crucial. It's one of the main things preventing the neutron star from collapsing further into a black hole. At slightly longer distances, the force is attractive. It pulls neutrons toward each other. This attraction is what holds ordinary nuclei together. But the interaction also depends on the relative orientation of the neutron's spins, on their relative motion, on whether they're approaching head-on or at an angle, and on the presence of other neutrons nearby. In an ordinary atomic nucleus, which contains at most a few hundred nucleons, physicists can model these interactions with reasonable accuracy. Nuclear physics has developed sophisticated techniques for calculating the properties of nuclei based on the forces between individual nucleons. But a neutron star's core contains roughly 10 to the 57 neutrons. That's a billion, trillion, 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 trillion particles, all interacting through a force that is immensely complicated, even between just two particles. Computing the exact behavior of this system from first principles is completely beyond our current capability. It may be beyond any conceivable computational capability. The problem is simply too vast, too complex, too many interacting particles with too complicated a force between them. Instead, physicists use approximations. They develop what's called an equation of state, a mathematical relationship describing how the pressure of nuclear matter depends on its density. The equation of state is the single most important piece of physics for understanding neutron stars. It tells you everything. Given the equation of state, you can calculate a neutron star's maximum mass, its radius, how its density varies from the surface to the center, how it deforms when spinning or when in a binary system. The equation of state is the key to everything. But here's the problem. We don't know the equation of state with confidence at the densities found inside neutron stars. We can measure the properties of nuclear matter at normal nuclear density, the density inside an ordinary atomic nucleus, because we can study nuclei in laboratories. We can accelerate nuclei and smash them together in particle colliders. We can observe how nuclear matter behaves under controlled conditions. But the densities in the core of a neutron star are 2, 3, 5, perhaps even 10 times higher than normal nuclear density. No laboratory has ever created cold, dense matter at these conditions. Heavy ion colliders like the ones at Brookhaven National Laboratory and CERN create incredibly dense matter by smashing heavy nuclei together at near light speed. But the matter produced in these collisions is extremely hot, thousands of billions of degrees, nothing like the relatively cold, dense matter in a neutron star's core. The physics of hot, dense matter and cold, dense matter are very different, governed by different aspects of the strong force. So even our most powerful particle colliders don't directly tell us what we need to know. This means that the equation of state inside a neutron star must be calculated theoretically, extrapolated from what we know at lower densities, and tested against astronomical observations. Different theoretical approaches give different equations of state. Some predict that neutron stars can be quite large, 25 or 30 kilometers across. Others predict they should be more compact, perhaps only 18 or 20 kilometers across. Some predict a maximum neutron star mass of about 2 solar masses. Others allow masses up to 2.5 or even 3 solar masses before the star would collapse into a black hole. The uncertainty is real and significant. This is one of the major open questions in nuclear physics and astrophysics. What is the equation of state of dense nuclear matter? What happens when you compress nuclear matter to several times its normal density? How does the strong force behave in a regime we've never been able to test directly? These are not abstract academic questions. They determine the structure and fate of some of the most extreme objects in the universe. They determine whether a collapsing stellar core becomes a neutron star or a black hole. They determine how large neutron stars are, how massive they can be, and what happens when two of them collide. Getting the equation of state right is one of the central challenges of 21st century physics. But before we reach the deepest interior, where the densities are highest and the uncertainties are greatest, there's a remarkable region we need to explore: the transition zone between the crust and the core. Because in this transition zone, matter does something truly bizarre, something that has no parallel anywhere else in physics. It forms structures that physicists have nicknamed nuclear pasta. Remember what the inner crust looks like: enormous neutron-rich nuclei, swollen far beyond their normal size, sitting in a sea of free neutrons and degenerate electrons. As you go deeper, the nuclei get bigger and bigger, while the neutron fluid between them gets denser and denser. The nuclei are approaching each other, the spaces between them are shrinking. At some point, the nuclei are so large and so close together that they almost touch. Now inside a nucleus, the dominant force is the strong nuclear force, which pulls nucleons together. Outside the nucleus, the spaces between nuclei are governed largely by the Coulomb force, the electromagnetic repulsion between the positively charged protons in neighbouring nuclei. These two forces, nuclear attraction and electromagnetic repulsion, compete with each other, and in the transition zone between the crust and the core, they compete in a way that produces extraordinary geometric structures. At relatively low densities in the inner crust, the nuclei are roughly spherical. This is the shape you'd expect. Surface tension from the strong force pulls nuclear matter into spheres, just as surface tension pulls water into droplets. A sphere minimizes the surface area for a given volume, which minimizes the surface energy cost. The spheres sit in a lattice, surrounded by the neutron gas. This is sometimes called the meatball phase, because you have roughly spherical lumps of nuclear matter embedded in a surrounding fluid. It's the most familiar configuration, the one that most closely resembles ordinary nuclei, just scaled up enormously. As density increases, the spheres grow larger and the spaces between them shrink. At a certain critical density, the spheres are so large and so close that it becomes energetically favorable for them to merge along one direction, forming long cylindrical tubes of nuclear matter running through the neutron fluid. Imagine spaghetti, long tubes of dense nuclear material embedded in a less dense surrounding medium. This is the spaghetti phase. The geometry has shifted from zero-dimensional blobs to one-dimensional strands because the balance between surface energy and Coulomb energy has tipped. Go deeper still, and the cylinders merge along a second direction, forming flat sheets of nuclear matter. These sheets are separated by layers of lower density neutron fluid. If you could somehow slice through this region, you'd see alternating layers of dense and less dense material, like sheets of pasta layered in a dish. This is the lasagna phase. At even higher densities, the geometry inverts. Instead of nuclear matter forming structures embedded in a neutron fluid, the neutron fluid begins forming structures embedded in the nuclear matter. First, you get cylindrical tubes of neutron fluid running through a continuous medium of nuclear matter. This is the anti-spaghetti phase, sometimes called the bucatini phase, named after the tubular pasta. Finally, at the highest densities of the transition zone, you get spherical bubbles of neutron fluid embedded in nuclear matter. This is the Swiss cheese phase, or the anti-meatball phase. Spherical holes in a continuous nuclear medium, and then, at densities just above this, the bubbles shrink and disappear, and you're left with a uniform nuclear fluid. The crust has ended. The core has begun. The pasta phases are the transition between two fundamentally different states of matter, from a crystalline solid with identifiable nuclei to a continuous quantum fluid. Nuclear pasta might sound whimsical, and the naming certainly is, but the physics behind it is deadly serious. These structures arise from a genuine competition between fundamental forces. The strong force prefers to clump nuclear matter together. Electromagnetism prefers to spread the positively charged protons apart. At the densities in the transition zone, these forces are nearly perfectly balanced, and the resulting structures are a compromise between them. The specific geometry at each density represents the configuration with the lowest total energy, the arrangement that minimizes the combined cost of strong force surface energy and electromagnetic repulsion energy. Nuclear pasta is thought to be incredibly strong. Calculations suggest it may be the strongest material in the universe, roughly 10 billion times stronger than steel. This isn't because of any exotic new force. It's because the structures are held together by the strong nuclear force itself, the most powerful force known at short distances. Breaking a sheet of nuclear lasagna would require overcoming the strong force's grip on every nucleon in the structure. The energy required would be staggering. The pasta phases also affect how the neutron star behaves in observable ways. The irregular geometry of the pasta may scatter neutrinos in ways that affect how quickly a newly born neutron star cools down after its formation in a supernova. The mechanical properties of the pasta may affect how the crust deforms under stress, which influences whether and how the star experiences sudden rotational glitches, brief episodes where the star's spin rate abruptly changes. Understanding nuclear pasta is directly relevant to interpreting astronomical observations. Now let's move past the pasta and into the outer core itself. Here the matter is a uniform fluid of mostly neutrons, with that small admixture of protons and electrons. And in this fluid, something extraordinary happens. The neutrons form a superfluid. A superfluid is a state of matter that flows with absolutely zero viscosity, no friction, no resistance to flow whatsoever. Once a superfluid begins moving, it continues moving forever without any energy loss. This sounds impossible, and for centuries physicists would have said it was impossible, but it's an observed phenomenon, confirmed in laboratories around the world. It was first discovered in 1938, when physicist Piotr Kapitsa in Moscow and independently John Allen and Don Misner in Cambridge found that liquid helium-4, when cooled below about 2.2 degrees above absolute zero, transitions into a superfluid state. The transition is sharp and dramatic. Above the critical temperature, helium behaves like an ordinary liquid. Below it, everything changes. Superfluid helium exhibits remarkable properties. It can climb the walls of its container, seemingly defying gravity, creeping upward in a thin film and dripping off the outside. It can flow through microscopic channels that would completely block any normal fluid. It has infinite thermal conductivity, meaning heat spreads through it essentially instantaneously. Superfluidity occurs because of quantum mechanics. Helium-4 atoms are bosons, particles that can all occupy the same quantum state, so they condense directly into a superfluid. But fermions, like neutrons, face a problem. The Pauli exclusion principle forbids them from sharing quantum states. The solution is Cooper pairing, named after physicist Leon Cooper. Two fermions combine together into a pair that behaves as a boson, a fundamentally different type of particle that is not subject to the exclusion principle. Many bosons can occupy the same quantum state simultaneously, so once enough pairs form, they can all condense together. When a large fraction of particles form Cooper pairs, and those pairs all occupy the same quantum ground state, the result is a superfluid, or, in the case of charged particles, a superconductor. In the outer core of a neutron star, the neutrons pair up through an attractive component of the strong nuclear force. At the relevant densities, neutrons interact with each other in a way that has a net attractive channel at certain relative momenta. This attraction allows neutron-Cooper pairs to form. When enough neutrons have paired up and the pairs condense into the same quantum state, the neutron fluid becomes superfluid. This isn't speculation. We have observational evidence that neutron star interiors are superfluid. The evidence comes from glitches. A glitch is a sudden, abrupt increase in a neutron star's rotation rate. Neutron stars are incredibly precise rotators. Their spin rates can be measured with extraordinary accuracy using radio telescopes that detect the regular pulses of radiation they emit. Over time, neutron stars gradually slow down as they lose rotational energy through magnetic braking. But occasionally, a neutron star's spin rate suddenly jumps upward by a tiny but measurable amount. These jumps happen on timescales of seconds or less. The most widely accepted explanation for glitches involves the superfluid interior. Here's the idea. The outer crust of the neutron star is a rigid solid, a crystalline lattice. It rotates as a solid body, gradually slowing down due to electromagnetic energy loss. But the superfluid in the interior doesn't have to slow down at the same rate because it has no viscosity. A superfluid can only rotate by forming quantized vortices, tiny whirlpools of circulation, each carrying a specific quantized amount of angular momentum. As the crust slows down, the superfluid maintains its rotation rate. A lag builds up between the crust's rotation and the superfluid's rotation. Eventually, the lag becomes large enough that the vortices in the superfluid suddenly unpin from the crust, transferring angular momentum to the crust in a catastrophic event. The crust speeds up. The superfluid slows down slightly. The two come back into closer alignment, and the process starts over. This is a glitch. It's the superfluid interior suddenly dumping angular momentum into the solid crust. The fact that we observe glitches with precisely the characteristics predicted by this model is strong evidence that the interior of neutron stars is indeed superfluid. The Vela pulsar, a neutron star about 1,000 light-years from Earth in the constellation Vela, is one of the most prolific glitches known. It was formed in a supernova explosion roughly 11,000 years ago, and it experiences a major glitch roughly once every 3 years. Each glitch increases its spin rate by about 1 part in a million. That might sound tiny, but for an object spinning roughly 11 times per second, with a moment of inertia vastly larger than any object on Earth, it represents an enormous transfer of angular momentum. After each glitch, the pulsar gradually recovers, slowly returning toward its pre-glitch spin-down rate over days to weeks, before eventually experiencing another glitch years later. This cyclic behavior of slow spin-down, sudden speed-up, gradual recovery, repeated over decades, is beautifully consistent with the superfluid vortex model. The protons in the outer core, though they make up only about 5% of the matter, also do something remarkable. They form their own Cooper pairs and become superconducting. Superconductivity is to electrical current what superfluidity is to fluid flow. A superconductor carries electrical current with zero resistance. Current flows forever without any energy loss. In a neutron star's outer core, the proton superconductor interacts with the star's magnetic field in complex ways. Magnetic flux is confined to quantized flux tubes, thin filaments of magnetic field threading through the superconducting proton fluid. These flux tubes interact with the neutron's superfluid vortices, creating a tangled, dynamic system of quantized structures that influences how the magnetic field evolves over time, and how the star's rotation couples to its magnetic behavior. This gives us a picture of the outer core that is profoundly strange. It's a quantum fluid, a vast ocean of superfluid neutrons threaded with quantized vortex lines, interpenetrated by a smaller population of superconducting protons carrying quantized magnetic flux tubes, with a background of degenerate electrons maintaining electrical neutrality. All three components coexist in the same volume, interacting through the strong force, the electromagnetic force, and the weak force. The neutrons flow without friction. The protons carry current without resistance. The electrons scatter off both, mediating interactions between the two quantum condensates. Nothing in your everyday experience corresponds to this, not even close. The closest laboratory analogue is superfluid helium, or superconducting metals cooled to near absolute zero in carefully controlled experiments. But those are simple systems compared to the outer core of a neutron star. Here, you have two interpenetrating quantum fluids existing at densities hundreds of trillions of times greater than any material on Earth, under pressures that would crush any laboratory apparatus into subatomic particles, threaded with magnetic fields a trillion times stronger than Earth's, all spinning hundreds of times per second. And the temperatures inside a neutron star are worth noting. A newly formed neutron star is incredibly hot, roughly 100 billion degrees at birth. But neutron stars cool rapidly by astronomical standards. Within minutes of formation, neutrino emission drops the core temperature to roughly 1 billion degrees. Over the following thousands of years, the temperature drops further. A neutron star that's a few thousand years old might have a core temperature of roughly 100 million degrees. One that's 1 million years old might have cooled to roughly 1 million degrees. These temperatures sound hot by human standards. 100 million degrees is far hotter than the core of the Sun. But in the context of the energies involved in neutron star physics, these are effectively cold. The thermal energy of the particles is tiny compared to their Fermi energy, the energy of the highest occupied quantum states. This is what allows superfluidity and superconductivity to exist. Despite temperatures of millions of degrees, the neutron star interior is quantum mechanically cold. The particles behave as though they're near absolute zero because the relevant energy scale, the Fermi energy, is so enormously high that thermal energies are negligible by comparison. A neutron star core at 100 million degrees is far colder, in the quantum mechanical sense, than liquid helium at 2 degrees above absolute zero. This is deeply counterintuitive. 100 million degrees sounds unimaginably hot, and it is, by everyday standards. But physics doesn't care about everyday standards. What matters is the ratio of thermal energy to Fermi energy, and in a neutron star, that ratio is tiny. The system is deeply degenerate, meaning quantum mechanical effects completely dominate thermal effects. This is why the superfluid and superconducting states can exist at temperatures that would vaporize anything on Earth. All of this, the neutron superfluid, the proton superconductor, the nuclear pasta in the transition zone, the elaborate force balance maintaining beta equilibrium, represents our best current understanding of the outer core of a neutron star. It's a picture built from nuclear physics, extrapolated to densities we've never directly tested, constrained by astronomical observations, and refined by decades of theoretical work. It's impressive, it's detailed, it's almost certainly at least partially correct. But it's also the easy part, because the outer core, strange as it is, involves matter at densities of roughly 1 to 2 times normal nuclear density. These are densities where our theoretical tools, while strained, are still on somewhat familiar ground. We're dealing with neutrons and protons interacting through the strong force. We understand these particles. We've studied them extensively. We know their properties, their interactions, their behavior in nuclei. We're extrapolating, yes, but we're extrapolating from a base of solid knowledge. The inner core is different. It's where the real mystery begins. The inner core begins where densities climb above roughly 2 times normal nuclear density and may reach 5, 8, perhaps even 10 times nuclear density at the very center. These are densities so extreme that the average distance between neutrons is significantly smaller than a neutron's own radius. Think about what that means. The particles aren't just close together, they're overlapping. They're being compressed into each other, forced to share the same physical space. At these densities, the concept of an individual neutron as a distinct object begins to lose meaning. The neutrons are composite particles, each made of 3 quarks held together by gluons. When you squeeze neutrons so close together that they overlap, the quarks inside one neutron start to interact directly with the quarks inside neighboring neutrons. The internal structure of the neutrons becomes relevant. You can no longer treat them as simple, indivisible objects. And this is where everything we thought we understood starts to break down. Because at these densities, matter may begin transforming into something that is no longer describable as neutrons and protons at all. Something fundamentally different. Something that takes us to the deepest open question in nuclear physics, and to the boundary of what we currently know about the nature of matter itself. At the outermost regions of the core, we could still describe the matter as neutrons. Individual particles, each one a distinct object with its own identity, interacting with its neighbours through the strong force. But as we descend deeper, as density climbs to 3, 4, 5 times the density of an atomic nucleus, this description starts to crack. Because a neutron is not a fundamental particle. It's not an indivisible building block. A neutron has internal structure. It's made of smaller things. And when you squeeze neutrons hard enough, that internal structure starts to matter in ways it never does under ordinary conditions. A neutron is made of 3 quarks, specifically 1 up quark and 2 down quarks, bound together by the strong nuclear force. The force binding these quarks is carried by particles called gluons, and the theory describing their interaction is called quantum chromodynamics, often abbreviated QCD. It's one of the most successful and mathematically rigorous theories in all of physics, and it tells us something remarkable about how quarks behave. Unlike electromagnetism, where the force between 2 charged particles gets weaker as they move apart, the strong force between quarks gets stronger as they're separated. This is one of the most counterintuitive features of the strong force, and one of the most important. Imagine stretching a rubber band between 2 fingers. The farther apart you pull your fingers, the harder the band pulls back. The strong force works similarly, but more extremely. Try to pull 2 quarks apart, and the force between them increases without limit. It increases so much that you can never actually isolate a single quark. If you try to pull a quark out of a neutron by injecting enormous amounts of energy, the energy you invest in pulling becomes so enormous that it spontaneously creates new quarks from the vacuum. The energy literally materializes into matter, into quark-antiquark pairs that immediately bind into new composite particles. Instead of freeing one quark, you end up with additional particles. The original quark never comes out alone. This phenomenon is called confinement, and it has been verified in countless experiments at every particle accelerator ever built. Under normal conditions, quarks are permanently confined inside composite particles like protons and neutrons. You never see a free quark wandering through space on its own. It simply doesn't happen. Not at room temperature, not in the core of a star, not in any environment humans have ever created under ordinary conditions. Every quark you've ever heard about, every quark that has ever participated in any physical process you could observe, has been locked inside a larger particle. But here's where it gets interesting. Confinement is a feature of the strong force at ordinary densities and temperatures. At sufficiently extreme conditions, confinement may break down. We have evidence for this from one direction. At extremely high temperatures, the kind created in heavy ion collisions at particle accelerators like the relativistic heavy ion collider at Brookhaven National Laboratory and the Large Hadron Collider at CERN, nuclear matter undergoes a phase transition. When gold or lead nuclei are smashed together at nearly the speed of light, the collision creates a tiny fireball with temperatures exceeding several trillion degrees. At these temperatures, protons and neutrons dissolve. The quarks and gluons that were confined inside individual nucleons break free and form a new state of matter called a quark-gluon plasma. In this state, quarks and gluons move freely over distances much larger than a single nucleon. Confinement has ended. The boundaries between what used to be individual protons and neutrons have dissolved, and you're left with a soup of liberated quarks and gluons. This has been experimentally confirmed. The quark-gluon plasma was first convincingly produced at the relativistic heavy ion collider in 2005, and subsequent experiments at the Large Hadron Collider have studied its properties in considerable detail. It behaves as a nearly perfect fluid, with extraordinarily low viscosity, one of the most perfect fluids ever observed. Its properties match theoretical predictions from quantum chromodynamics remarkably well. But the quark-gluon plasma produced in colliders is extremely hot, trillions of degrees. It exists for only the tiniest fraction of a second before the fireball expands, cools, and the quarks and gluons recombine into ordinary hadrons, the family of composite particles that includes protons and neutrons. The conditions inside a neutron star's inner core are fundamentally different. The densities are comparable, perhaps even higher, but the temperature is vastly lower. 1,000,000 degrees might sound hot, but compared to the relevant energy scales in quantum chromodynamics, it's effectively zero. The inner core of a neutron star, if it contains deconfined quark matter, would represent a completely different region of the QCD phase diagram than what colliders explore. It would be cold, dense quark matter, as opposed to the hot, dense quark matter created in accelerator experiments. And this is where theoretical physics runs into a wall. Quantum chromodynamics is extraordinarily difficult to calculate in the cold, dense regime. At high temperatures, theorists have developed powerful computational techniques, particularly lattice QCD, which uses supercomputers to simulate the behavior of quarks and gluons on a discrete space-time grid. Lattice QCD has been tremendously successful at calculating the properties of the quark-gluon plasma and matching those calculations to experimental results from heavy ion colliders. But lattice QCD has a fundamental mathematical obstruction in the cold, dense regime. It's called the fermion sign problem, and it renders the standard computational approach essentially useless at the densities relevant to neutron star interiors. The sign problem is technical, but its consequence is simple and devastating. We cannot reliably compute the properties of cold, dense quark matter from first principles, using our best theory of the strong force. We have the theory. Quantum chromodynamics is believed to be the correct and complete theory of the strong interaction. We just can't solve it in the regime that matters most for neutron stars. This is not a failure of physics, it's a limitation of mathematics and computation. The equations are there, we just can't extract the answers. This means that the question of what exists in the innermost core of a neutron star, whether the matter is still in the form of neutrons or has transitioned to deconfined quarks, or something else entirely, remains genuinely open. Physicists have proposed several possibilities, each grounded in theoretical reasoning, but none definitively confirmed. The first possibility is that the matter remains in the form of neutrons all the way to the center. In this scenario, even at 5 or 8 times nuclear density, the neutrons are squeezed and overlapping, but still maintain their identity as individual 3-quark objects. The strong force's short-range repulsion between quarks in different neutrons prevents complete dissolution. The equation of state is stiff, meaning the pressure rises sharply with density, and the neutrons push back hard enough to resist further compression without losing their individual character. This would make neutron star interiors extreme, but conceptually straightforward. Dense nuclear matter pushed to its limits but still recognizable. The second possibility is deconfinement. At some critical density in the inner core, the boundaries between neutrons dissolve. The quarks that were confined inside individual neutrons suddenly find themselves able to roam freely across macroscopic distances. Instead of 3 quarks locked inside each neutron, you have a vast sea of free quarks and gluons, a cold, dense quark-gluon plasma filling the innermost region of the star. This would be a genuine phase transition, as dramatic in its way as the transition from liquid water to steam, or from ice to liquid water. A fundamental reorganization of how matter is structured. On one side of the transition, identifiable neutrons. On the other, liberated quarks. The identity of the neutron as a distinct particle would be gone, replaced by a continuous quark fluid, where no individual nucleon can be identified, any more than you can identify an individual water molecule in the ocean by looking at the waves. Some theoretical models predict this transition happens sharply at a specific density, a clear boundary between hadronic matter and quark matter. Others predict a smooth crossover, where neutron identity gradually fades, rather than disappearing at a definitive threshold, a slow dissolution, rather than a sudden break. If deconfined quark matter exists in the core, it would be a truly extraordinary form of matter. The quarks involved would primarily be up quarks and down quarks, the same flavors found in ordinary protons and neutrons. But there's a third possibility that makes things even stranger. Up and down quarks are the two lightest quarks in nature. There are actually 6 flavors of quarks in total: up, down, strange, charm, bottom, and top. The heavier quarks, charm, bottom, and top, are far too massive to play any role at neutron star densities. Their masses are so high that the energy cost of producing them exceeds what's available even under these extreme conditions. But the strange quark is different. It's heavier than up and down quarks, but not enormously so. The strange quark has a mass of roughly 95 million electron volts, compared to about 2.2 million electron volts for the up quark, and about 4.7 million electron volts for the down quark. The strange quark is roughly 20 to 40 times heavier than the light quarks, which sounds like a lot, but at the densities and energies available in a neutron star's inner core, this mass difference might be manageable. In a cold, dense quark matter environment, the Fermi energies of the up and down quarks can become high enough that it's energetically favorable to convert some of them into strange quarks. The reasoning goes like this. If you have a sea of up and down quarks filling up energy states, the Pauli exclusion principle forces each additional quark into a higher energy state. At some point, the cost of adding another up or down quark to an already crowded energy level exceeds the cost of simply producing a strange quark, which can start filling its own empty energy levels from the bottom. The system can lower its total energy by spreading the quarks across 3 flavors instead of 2, even though strange quarks are individually heavier. It's more efficient to have 3 partially filled pools than 2 overfilled ones. If this happens, the inner core would contain strange quark matter, a roughly equal mixture of up, down, and strange quarks, forming a 3-flavor quark plasma. This hypothesis was developed independently by several physicists in the 1970s and 80s, including Edward Witten, who in 1984 proposed something even more radical. Witten suggested that strange quark matter might not just be a phase that appears under extreme pressure, it might be the true ground state of matter, the lowest energy configuration, more stable than ordinary nuclear matter, more stable than iron, which we currently believe is the most stable form of ordinary matter per nucleon. If Witten's hypothesis is correct, then a lump of strange quark matter, once formed, wouldn't decay back into neutrons. It would stay as strange quark matter indefinitely, because it's already in the lowest possible energy state. There would be no lower energy state for it to decay into. Ordinary matter, the protons and neutrons that make up everything around you, every rock and tree and planet and star, would be metastable. Not truly stable, but trapped in a local energy minimum, separated from the true ground state by an energy barrier. It could, in principle, convert to strange quark matter if given a sufficient push to overcome that barrier, much as diamond is metastable relative to graphite. Diamond can persist indefinitely under normal conditions, even though graphite has lower energy, because there's an energy barrier preventing the spontaneous conversion. Your body, in this scenario, is like a diamond, stable for all practical purposes, but not in the absolute lowest energy state that matter can achieve. This leads to a remarkable possibility. If strange quark matter is the ground state, then some neutron stars might not be neutron stars at all. They might be strange stars, objects made entirely or almost entirely of strange quark matter from their centers to their surfaces. A strange star would look very different from a conventional neutron star. It would have a sharp surface where the quark matter meets the vacuum, rather than the gradual layered structure of crusts and cores we've been describing. It might be slightly smaller, or have a different relationship between mass and radius. The differences would be subtle, but potentially detectable with sufficiently precise observations. Whether strange quark matter is truly the ground state remains unknown. The answer depends on the detailed properties of the strong force at densities and energy scales where we simply cannot perform reliable calculations. Different theoretical models give different answers. Some predict strange quark matter is stable, others predict it isn't. The question is genuinely open. There are also other exotic possibilities beyond quark matter. At sufficiently high densities, quarks might pair up in a phenomenon analogous to the Cooper pairing we discussed for neutrons and protons. When electrons form Cooper pairs in metals, the result is superconductivity, the flow of electrical current without any resistance. When quarks form Cooper pairs, the result is called color superconductivity, named after the color charge that quarks carry in quantum chromodynamics. Just as electric charge comes in positive and negative, quark charge comes in three types whimsically called red, green, and blue. Color superconducting quark matter would have remarkable properties that go far beyond ordinary superconductivity. The quark pairs would form a condensate, a macroscopic quantum state with unique transport and electromagnetic characteristics that are unlike anything observed in any material on Earth. Several different color superconducting phases have been predicted theoretically, each with its own distinctive pairing pattern and symmetry structure. The most symmetric, called the color flavor locked phase, pairs quarks of all three light flavors and all three color charges in a maximally symmetric arrangement that simultaneously breaks multiple symmetries of the strong force in a beautifully coordinated way. Whether any of these phases actually exist inside neutron stars depends, again, on details of the strong force that we cannot currently compute from first principles. Some theoretical models have also proposed the appearance of hyperons in the deep interior. Hyperons are particles similar to protons and neutrons, but containing one or more strange quarks while still being confined composite objects, not free quarks. A lambda hyperon, for example, contains one up quark, one down quark, and one strange quark. Under sufficient pressure, it might become energetically favorable for some neutrons to convert into hyperons, introducing strangeness into the core without full deconfinement. This is sometimes called the hyperon puzzle, because many equations of state that include hyperons predict neutron star maximum masses that are too low to match the most massive neutron stars we've actually observed. The heaviest confirmed neutron stars have masses around 2 solar masses, and some hyperon-containing models can't support that much weight. Resolving this puzzle is an active area of research. So what do we actually know? With so much theoretical uncertainty, how do we make progress? The answer is observations. Neutron stars might be the only laboratories in the universe where these conditions naturally exist, and astronomers have developed increasingly powerful ways to study them. The most direct constraint comes from measuring neutron star masses. If we know how heavy a neutron star can be, that immediately rules out equations of state that predict a lower maximum mass. The most precisely measured heavy neutron star is PSRJ 0348 plus 0432, a millisecond pulsar discovered in 2007. Its mass has been measured at roughly 2.01 solar masses, using a technique called Shapiro delay, which measures how the pulsar's radio signals are slowed as they pass through the gravitational field of its companion white dwarf. This measurement rules out any equation of state that predicts a maximum mass below about 2 solar masses. Many soft equations of state, including some that include hyperons or early onset of quark deconfinement, are eliminated by this single observation. Other heavy neutron stars have been measured since then, further constraining the possibilities. PSRJ 0740 plus 6620, discovered in 2019, has a mass of roughly 2.14 solar masses with relatively small uncertainty. These observations tell us that whatever the equation of state is, it must be stiff enough to support roughly 2 solar masses against gravitational collapse. This is a powerful constraint. Radius measurements provide complementary information. NASA's Neutron Star Interior Composition Explorer, known as NISA, is an X-ray telescope mounted on the International Space Station, specifically designed to measure neutron star radii with unprecedented precision. By analysing the pattern of X-ray emission from hotspots on the surfaces of rotating neutron stars, accounting for how the star's intense gravity bends and distorts the light, NASA can determine both the mass and radius of the same object simultaneously. The results from NASA's first targets suggest neutron star radii of roughly 12 to 13 kilometers for stars of about 1.4 solar masses. This is consistent with a moderately stiff equation of state, neither too soft nor too hard. But perhaps the most spectacular constraint came on August 17, 2017, when the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars for the first time. The event, designated GW170817, was one of the most important astronomical observations in history. It was also one of the most widely observed. Within seconds of the gravitational wave detection, alerts were sent to observatories around the world, and within hours, more than 70 telescopes on every continent and in space had turned to observe the aftermath of the collision. It was the first time a cosmic event had been observed in both gravitational waves and electromagnetic radiation, opening an entirely new era in astronomy called multi-messenger astrophysics. As the two neutron stars spiraled toward each other in the final seconds before collision, the gravitational waves they emitted carried detailed information about their internal structure, specifically the tidal deformability. The degree to which each star was distorted and stretched by the gravitational field of the other as they drew closer and closer together depends directly on the equation of state. A star that's easy to deform, one that stretches and bulges significantly under tidal forces, has a soft equation of state. A star that resists deformation and maintains its spherical shape even under extreme tidal stress has a stiff one. The imprint of this deformation is encoded in the gravitational wave signal during the last few orbits before the collision, and LIGO was sensitive enough to measure it. The gravitational wave signal from GW170817 showed that the neutron stars were moderately deformable, neither perfectly rigid nor extremely squishy. This constrained the equation of state from yet another direction, ruling out extremely stiff models where the stars would barely deform and extremely soft models where the stars would deform dramatically. The measurement was consistent with the mass and radius determinations from NICER, narrowing the range of possible equations of state. The electromagnetic observations of GW170817 were equally valuable. The collision produced a burst of gamma rays detected by the Fermi Space Telescope roughly 1.7 seconds after the gravitational wave signal. This confirmed that neutron star mergers produce short gamma ray bursts, a connection that had been suspected for decades but never proven. In the hours and days following the merger, telescopes across the world observed a new type of transient called a kilonova, a thermal glow powered by the radioactive decay of heavy elements freshly synthesized in the merger debris. The kilonova provided direct evidence that neutron star mergers are a major site for the production of heavy elements through the rapid neutron capture process, known as the R process. Elements like gold, platinum, uranium, and thorium, heavy atoms that cannot be created in ordinary stellar fusion because they sit above iron on the nuclear binding energy curve, are forged in the extreme neutron-rich conditions of neutron star mergers. Spectroscopic analysis of the kilonova confirmed the presence of lanthanide elements in the debris, heavy rare earth elements that require enormous neutron fluxes to create. The gold in any ring you might wear, the platinum in a catalytic converter, the uranium that powers nuclear reactors, all of it was likely created in a neutron star collision billions of years ago, scattered into the interstellar medium, incorporated into the gas cloud that formed our solar system, and eventually concentrated in Earth's crust by geological processes over billions of years. Future gravitational wave observations promise even tighter constraints. LIGO and Virgo have been upgraded, and new detectors are planned. The next generation of gravitational wave observatories, including the Einstein telescope planned for Europe and Cosmic Explorer proposed for the United States, will be roughly 10 times more sensitive than current detectors. They will observe neutron star mergers at much greater distances, detecting hundreds or thousands of events per year instead of a handful. Each event provides another measurement of tidal deformability, another data point constraining the equation of state. With enough events, the statistical power will be enormous. We may be able to determine the equation of state with sufficient precision to distinguish between models with and without quark deconfinement. We may be able to tell whether the inner core of a neutron star contains exotic matter, or whether neutrons persist all the way to the center. There's something profound about all of this. We're trying to answer one of the deepest questions in physics. What happens to matter at the most extreme densities the universe can produce? And we're doing it not by building impossibly powerful particle accelerators, not by recreating these conditions in a laboratory, because we can't. We're doing it by watching the sky. By listening to the gravitational ripples from colliding neutron stars billions of light years away, by catching X-ray photons from spinning pulsars and decoding the geometry of their surfaces, by measuring the masses of neutron stars in binary systems with exquisite precision, using nothing more than the timing of radio pulses traveling across the galaxy. Neutron stars are the universe's own laboratories. They create conditions we could never hope to reproduce. They compress matter to densities we cannot achieve. They sustain those conditions not for the fleeting microseconds of a heavy ion collision, but for billions of years. And they broadcast information about their interiors across the cosmos, in gravitational waves, in X-rays, in radio pulses, in the light of kilonovae. We just have to be clever enough to read the signals. And that is ultimately the story of what happens inside a neutron star. It's the story of matter being pushed to the edge of what it can endure. At the surface, atoms are crushed, their electrons stripped away, and their nuclei packed into a lattice denser than anything on Earth. Deeper, electrons are driven into protons, producing a flood of neutrons that overwhelms all other particles. Deeper still, the nuclei themselves dissolve, their boundaries meaningless in a sea of nuclear fluid that flows without friction and conducts without resistance. And at the very center, in the deepest and densest regions, even the neutrons may lose their identity. The quarks inside them may break free, forming a new state of matter that has no name in everyday language, a state that exists nowhere else in the universe, a state that we are only now beginning to detect and characterize through observations of the most extreme objects the cosmos has ever produced. The neutron star is 12 miles across. You could drive over it in a quarter of an hour. It weighs more than the sun. A teaspoon of its material would outweigh a mountain. Its gravity would crush you to a film of atoms. Its magnetic field could destroy every chemical bond in your body from 1,000 miles away. And inside it, the matter that makes up everything you've ever known, the atoms that form stars and planets and people, has been broken down into something unrecognizable, something that challenges our understanding of nature itself. The universe built these objects. It built them from the deaths of massive stars, from the most violent explosions in the cosmos. It filled them with matter compressed beyond anything our laboratories can achieve, and it left them spinning in the darkness, broadcasting their secrets in pulses of light and ripples in space-time, waiting for someone to figure out how to listen. We are just now learning how, and what we're hearing is telling us that matter, the stuff we thought we understood, still has secrets. Deep inside a neutron star, at the boundary of what physics can describe, matter is still surprising us. It's still breaking down into forms we never predicted, and the story of what it becomes when pushed to the absolute limit is still being written.